Right now, 150 kilometers of primordial darkness is rising beneath our solar system, and it's erupting. This isn't some distant asteroid. It traveled from 40,000 astronomical units, survived the galactic tide, and now it's positioned directly below us, spewing 1,000 kilograms of material per second. Darker than coal, bigger than any comet we've seen. Already breaking the rules by outbursting where nothing should. NASA's watching it, but are we ready for what happens when something this massive, this ancient, this active cuts through our orbital plane in 2033? Let's dive right in. Picture this. Two astronomers in 2014 scrolling through endless frames of old sky survey data. Tedious work. Most nights, nothing. But then they saw it, a moving dot that didn't belong in any catalog. When they traced it back through archival images to 2010, the trajectory told an impossible story. This thing came from 40,000 astronomical units away. That's 1,000 times further than Neptune. It had been drifting in the galactic tide, barely tethered to our sun's gravity, possibly for hundreds of thousands of years. Bernardinelli and Bernstein had just discovered something that would rewrite what we thought we knew about the edge of our solar system. Fast forward to today. That object, officially designated C/2014, UN-271, though let's just call it BB, is no longer at the edge. It's here, directly beneath our solar system, and it's doing things that comets aren't supposed to do. NASA classifies it as a comet, which feels inadequate the moment you see the numbers. Halley's Comet, the one everyone knows, 7 miles across. Hale-Bopp, that spectacular visitor from the 1990s, 46 miles. The previous record holder most people never heard of, 60 miles. BB, 85 miles in diameter. Hubble confirmed it in 2022. That's not a comet in any traditional sense. That's a dwarf planet pretending to be one. The only comparable object is Chiron, a 220-kilometer centaur that orbits between Jupiter and Saturn. But Chiron stays local, always within the sun's protective bubble. BB came from the dark between stars. What makes this especially unnerving is where it sits right now. Most objects in our solar system travel along roughly the same flat plane. Imagine a dinner plate with everything rolling around on it. BB's orbit is inclined 95 degrees to that plane. It's not just tilted, it's perpendicular. It dropped from above, passed straight through, and now sits directly underneath everything. The sun, all the planets, the entire inner solar system. The geometric angles this creates are unprecedented. We calculate planetary positions in 2 dimensions, but suddenly there's a third axis that actually matters, and we have no historical data for what happens when something this massive occupies this position. Then there are the eruptions. Comets follow rules. They stay frozen until they get close enough to the sun, then gradually warm up and start releasing gas and dust. Simple thermodynamics. Predictable. BB started violently outgassing at 26 astronomical units, nearly Neptune's orbit, where solar radiation is so weak that temperatures barely rise above absolute zero. Nothing should be happening out there. Every comet we've studied waits until it's much closer before showing any activity. Not this one. At 26 astronomical units, it began explosive outbursts. Over 100 million kilograms of material ejected in less than a day. And it hasn't stopped. Right now, this very moment, BB is losing 1,000 kilograms every second. That's a small car's worth of mass continuously ejecting into space. The composition includes carbon monoxide, carbon dioxide, and ammonia, volatiles that sublimate at extremely low temperatures. But here's the question keeping scientists awake. If it's doing this now, what happens when it gets 10 times closer to the sun's heat in 2031? When Hubble analyzed BB's surface, something else emerged that defied expectations. The albedo, the measure of how much light reflects off a surface, came back at 4%. 4%. That's darker than coal, darker than asphalt, darker than almost anything we've measured in the solar system. Our moon reflects about 12%. Most asteroids reflect 10 to 20%. This object absorbs 96% of all energy that hits it. Every photon from the sun, every particle from the solar wind, every bit of cosmic radiation, all of it absorbed, not reflected. Where does that energy go? Into heating the interior, into triggering more outgassing, into processes we don't fully understand because we've never seen anything like this. Here's where it gets even more complex. At 150 kilometers across, BB has real gravity. Not enough to hold an atmosphere, but absolutely enough to recapture some of the material it's ejecting. Normal comets lose their outgassed material permanently. It escapes into space, forming tails that stream away forever. But BB is massive enough that heavier dust particles get pulled back down after being ejected. Imagine materials sublimating, shooting upward from the explosive phase change, then curving back down like snow falling back to the surface. We've never witnessed dynamics like this. The object is simultaneously losing material and recapturing it, redistributing it, potentially triggering secondary eruptions when that material lands on warmer regions. We have no models for this, no previous observations to guide predictions. The current calculations put its closest approach to the Sun at 10.95 astronomical units in January 2031, just beyond Saturn's orbit. Most comets dive inside Earth's orbit. Some graze the Sun itself. But BB started erupting at 26 astronomical units and is currently outgassing intensely near Uranus at roughly 19 astronomical units. When it reaches 10 astronomical units, where solar energy is 4 times stronger, the official predictions show a modest brightness increase to magnitude 13, barely visible through amateur telescopes. But those predictions assume BB will behave like every comet we've studied. They assume linear responses to increasing heat. They assume the ultra-dark surface won't create runaway heating. They assume gravity won't trigger unexpected feedback loops. The truth is, BB has likely never been this close to the Sun before. Its previous journey took it out to 40,000 plus astronomical units. Its next one is calculated at 60,000 astronomical units. At those distances, the gravitational pull of the Milky Way itself, along with passing stars and rogue brown dwarfs, perturbs its orbit so much that long-term predictions become guesswork. We genuinely don't know what ancient primordial materials are locked in that ice, frozen since the solar system's formation. We don't know what happens when they warm up for the first time in potentially millions of years. Then comes August 8th, 2033. That's when BB crosses the ecliptic plane, punching straight through the orbital disk that contains all the planets. By then, it will have undergone whatever heating and outgassing occurs at perihelion, and it will be trailing debris. If it maintains even a fraction of its current 1,000 kilograms per second ejection rate over the next 8 years, we're looking at roughly 126 billion kilograms of primordial material spread across its path. When it crosses the ecliptic in 2033, that entire debris field crosses with it. What happens to material with that chemical composition when it interacts with the solar wind? Does it affect heliosphere dynamics? Could any of it eventually drift into the inner solar system? We're not even asking these questions yet, let alone answering them. What frustrates me most is that we have time. 6 years until perihelion, 8 until the crossing. That's enough to design and launch a flyby mission. One amateur enthusiast already calculated a viable trajectory using gravity assists from Earth and Venus, reaching BB by 2033 to 2034. The scientific value would be immeasurable: direct sampling of materials from deep interstellar space, analysis of primordial solar system composition, real-time observation of unprecedented outbursts, data that could revolutionize our understanding of planetary formation and interstellar chemistry. But there's no official mission, no public plans. We watched NASA fumble the 3I/Atlas opportunity, and now that Interstellar Visitor is fading, while Juno gets incinerated in Jupiter's atmosphere instead of being redirected for even a distant observation. So, what's really happening right now while BB sits beneath us? It's positioned perpendicular to everything in our solar system. It has measurable gravitational influence. It's actively hemorrhaging material with unknown chemical composition. It's absorbing energy at maximum efficiency with that 4% albedo. Solar wind particles interact with its debris field. The materials it's releasing, ammonia, CO, CO2, and compounds we haven't detected yet, are entering the lower heliosphere, potentially affecting chemistry in regions we barely monitor. And in 8 years, it cuts through the ecliptic plane during a solar minimum, when the sun's magnetic field is at its weakest. I'm not predicting catastrophe, but we're watching the most accessible ultra-deep space object of our lifetimes pass through the solar system, and we're treating it like a footnote. Here's what we know for certain. BB is 150 kilometers of primordial material from 40,000 astronomical units, positioned directly beneath us, erupting at distances that defy every comet model we have. It's darker than coal, absorbing 96% of all energy. It reaches perihelion in January 2031 and crosses our ecliptic plane in August 2033. What we don't know: whether those eruptions will intensify dramatically, whether virgin materials locked in that ice for millions of years will behave predictably when heated, whether the debris field it's trailing will interact with our solar system in ways we haven't considered. That uncertainty is exactly why I'll be covering every development, from brightness changes to potential mission proposals. This isn't just another space rock. This is a window into the primordial solar system, and it's active right now. If you want real-time updates as BB approaches perihelion, subscribe to Galactic Breaking News and hit that notification bell. Drop a like if this changed how you see our solar system's edge, and comment below. Do you think NASA will finally launch a Flyby mission, or will we watch another historic opportunity slip away? Check out our playlist on interstellar visitors for more objects breaking the rules. The next update drops soon. Don't miss it.